Okay, good afternoon. I'm very pleased to introduce Mr. Steve Battista from MITRE Corporation. He has really a long career in security. He has been working in this area for 20 years. So make sure you ask him a lot of questions. This is a good opportunity for you to interact with an expert in our field. So I leave the floor to Steve.
So if you ask me questions, I should appropriately answer them with a question. Because as you get advanced, you don't answer, you just, answer the questions. So today we're going to be investigating firmware and embedded controllers in machines. And I wanted to have kind of an overview that this is an emerging threat for this field. Really, from even when I started, firmware is getting a lot more complicated in machines. It really is part of the threat landscape that should be appreciated. What you see in a lot of operational environments are people that will re-image a disk, redo the operating system and say, machine uncompromised. And I think in the future that's going to become less common. Also, this is a very fast-moving area. And, these references that I have in the presentation are in the notes, and we'll be able to send those out. So there's like videos and papers you can read. But many of these references are from, Wikipedia, public social media, blogs, stuff like that. So it's not necessarily a very strong academic discipline yet. And part of my presentation here is to convince you that this is a great place to do research. If you're frustrated with dealing with, NX bits and COP and all kinds of the buffer overflow issues, you don't get as many of that in firmware, so it's much easier to work in that area. It is much more complex, but this is an area that's really ripe for research to have standard ways of dealing with things. So this is very complex. 10 to 20 years from now, you're going to look back and go, oh, that stuff is so obvious. But if I rated myself on the quality of the code that I wrote when I started 20 years ago, I would be completely in failure mode. So, this is really the time for research. So this is to paint this general landscape for you guys. It's not a rigorous engineering document, but to kind of give you an introduction into that area and say this is a really good area to start. So the obligatory agenda slide, we're going to talk about all these things. I have a tendency to talk quickly. And just to remember, a lot of this stuff is the foundation that your software runs on. Without that strong foundation, things lean over and cause problems. So mostly when I explain a computer to people, they think of it as a box. It is one chip, it is one thing, and it's not. There's a CPU, there's memory, there's PCI Express boards. Across the bottom, you see items such as the high-speed USB ports and the PCI ports. So when you really start to think of a computer, it is several different computers inside of it, of which you shouldn't trust all of them. So, in two scales, you see computer security. I'm not going to trust a large network of machines, and I can't trust what's inside the plastic box, because those things can be attacking you, and they may disagree. So really, one of the main things that I've seen in this field is the BIOS, which is a basic input-output system. So this actually started in the early 70s, before there was the chipset. They actually had it loaded from disk. And it was the thing that started your machine. It is the thing that wakes up first. And prior to the 90s, they were stored in read-only memory or PROM chips. But about 1995, they were built on EEPROM, which is electrical rewritable, read-only memory. So that's not necessarily read-only. And so therefore you could update these things. I don't know how many of you have laptops or desktops, whether you've ever updated your BIOS. Some of them do have security updates and feature updates. I'd recommend you doing it, but they're not really thought about. And so they've also originally started on the ISA bus, which was the card bus that had a lot of the normal components on it. They started moving to their own specialized bus in '97, this low pin count bus. In fact, there's a great presentation if you go look on YouTube of someone resetting the registers in a BIOS with a grounding wire using the LPC bus. And they've now moved them to the serial peripheral bus. And so they haven't really stayed in the same place. They've really changed over the years to the point that in 2008, ASUS develops a splash top Linux on some motherboards within this BIOS. One of the other caveats I definitely want to say is when I say particular vendors that are doing things, this is not a gotcha presentation. These guys should be lauded for working in this area. It's just so new that it is a good area to apply additional academic rigor in the science of security in this area. So what they did is they implemented actual Linux within the motherboard itself. So some of these BIOSes can be 4 gigs large. To me, when I started, that is an entire computer. So when you say that these things are small, it doesn't mean that they don't have anything in them. And in 2010, a new model of the BIOS started to come out, a new version, the UEFI version, and they included some things like cryptographic controls and defined network boot and stuff like that. When you look at some of these standards, they've become mostly de facto standards. They are not formal standards, and therefore they really do need to be rigorously looked at. So the first question you say is, that's great, now they know what's in a machine, what's the theoretical landscape from a threat point of view? Well, the first thing we should go back to is all the way in 1998. The Chernobyl or space filer virus actually allowed you to flash ROM from the user space. Now at that point, there was not, if you go back to Windows 95, there was not really good segmentation on who owned what. There wasn't like a special kernel space, user space, so you were allowed to do that. So as being a nuisance, they would reflash your BIOS as blank. If you had the ability to take it out, you could put it into another machine and flash it, otherwise your machine was pretty dead. So this really goes back to a long time. And in 2006, there's a great presentation that talks about implementing and detecting the power instance within BIOS to use those power controls to compromise the operating system on install. So the idea is that you have a compromised machine, you put a new operating system on it. This proof of concept will re-compromise the operating system on install. In 2007, you start to see more refined proof of concepts where, in the IceLord toolkit actually targeted award BIOSes for a persistent compromise. And in 2009, you start to see a paper and a presentation, the two 2009s are the same, dealing with this common decompression routine. So the idea is they moved it from a very specific for a BIOS implementation to the generic decompression routine used within BIOSes so they can possibly use it across multiple BIOS hardware sets. And they've created this 100-line Python injector tool in their presentation. So if you know some Python, you can write some malware that will survive an OS reboot. 2009, Invisible Things Lab, which by the way, excellent company for some of the research they did, actually compromised a signed version of the BIOS. This wasn't using TPM, but it was using digital signatures and hashes within the BIOS itself. What they realized is that the OEM image was not part of the signed copy of the BIOS, so that OEMs could load their own image. Well, what they did is they used a buffer overflow technique in the OEM image to execute code that they wanted to on the BIOS to actually have code executed on that BIOS. So it was very interesting. So even when security controls are put in place, they really do need to be examined. It makes sense so that OEMs can put their own image in without having to follow through a cryptographic process, but then you have to prepare that for dealing with buffer overflows. So then once you have these theoretical things, is there anything in the wild that you know of? Well, in 2011, and I will not pronounce it correctly because I've never heard anyone pronounce it, the Membrabi is the first BIOS rootkit in the world. It actually checks for the BIOS type, and if it is a compatible type, it sees if it's already compromised because it puts a flag in there so it doesn't do it again, and it reflashes the BIOS. Now I think it actually has to do a reboot to reflash the BIOS because there are controls in place. And in doing that, it actually compromises the master boot record, which is something that's the part of the operating system on the disk that's loaded before the OS, and it actually compromises the machine. It still only exists in the award BIOS, and there's some talk about why it isn't for the other BIOSes, but it may be that the IceLord did all the work for them. And this last part's a joke. You know it's real if there's a signature for it. Well, at least you know that that information is getting out and it's being sent amongst lots of people. Things can be real without a signature, but if there is a signature for it, you do know that operations people are seeing in the wild and they're trying to build signatures to detect these things at the network level as they're coming in. And these are some of the hash strings for the original non-obfuscated code or the original obfuscation of the code. It doesn't mean you'll guaranteed to catch them. One of the other areas that people really need to be concerned about are graphics processing units. And if you've ever been a gamer or known some gamers, these graphics processing units can be pretty beefy. They have a lot of ability. We're talking large amounts of memory bandwidth, and lots of cores. These GPUs have their own BIOSes and hang off of some of the south bridge or hang off parts of the motherboard and have access to data. And they have large amounts of compute power. Some of the newer browsers allow for GPU microcode execution. Some of them do have reference monitors, like Google Chrome, but Google Chrome paid $60,000 to someone who figured out how to run code on the GPU that has access to direct memory access within the hardware itself. So when you start looking at this from a high level, I've downloaded, this web page, and now I've gotten all the way into the firmware. It was very interesting compromise that person has. And if you're actually doing this work, you really don't have to go buy a bunch of GPUs to test it. You can rent these test beds from Amazon, as about right now the current price is $2.10 an hour. So if you're really looking for a test bed, my advice is, go rent one. There's no reason to buy cards and set up machines. Another common area that people are starting to look at that I think will become valuable in the future is the process control boards on the hard drive. So, these hard drive controllers manage all this data transfer, and some of them do crypto right there also, and have buffers and spindle speeds and head movements. So this is a very interesting place to put a piece of malware on this part of the compute area to either steal data or modify data. And if you look at flash drives, they're even more complex with sector remapping and all kinds of calculations that are going on. If you just even look at the error correction code that's going on in now modern hard drives, it's a lot of calculations. Then the last part, it's not necessarily firmware, but I've already talked about this, that the master boot record and the volume boot records exist outside the OS. And so they're a great place to load code that would survive a reimage if the disk wasn't wiped or the disk wasn't repartitioned correctly. And a great place to look up is the TDL4 rootkit, which has done some very interesting stuff to circumvent some of the controls in Windows 7 64-bit. So it's a good place to put code that's not necessarily firmware, but it's a good place to hide stuff. Guillaume has a very interesting proof of concept, and I don't know if he brought it to fruition, but he realized that there were EEPROMs within the network cards of machines. So what he did is he reverse engineered it so that he can do stuff at the network card level. And when you start to think about it, you now have a processor that has access to direct memory access and also has access to a network connection. And not only does it have access to a network connection, but it may have it at the analog level. So if you were going to steal data and you didn't want to use IPv4 or IPv6, you could use any variation of a covert channel at that point. And some of the cards actually include their own crypto chips because they're thinking of doing some of the crypto potentially in the cards. So you could use those crypto chips to obfuscate or encrypt your outgoing data. So, that is a very good place to put some malware that would compromise a machine. So in 2011, a very interesting attack that was shown, and I have links to actually a YouTube video and a paper on this, where they reflashed a keyboard that you'd plug in. And what this keyboard would do was exploit a buffer overflow in something called system management mode actually, and this system management mode allows you to control the CPU and execution of what's going on. It's very deep in the operating system. And by having a compromised keyboard plugged into a laptop, you can basically rootkit the CPU and rootkit the box itself. So, there are some future designs, and we'll talk about that later on how to try to prevent some of the things that are going on with dealing with this. But it's an interesting way of thinking of how to jump from an external entity to pretty much SMM has been called by Invisible Things a level -3 ring rootkit, where kernel was ring 0. So if you look up their presentations on this, it's very, very interesting. One of the things that is not firmware that's in the box, and I haven't seen this get to the point where it actually compromises the firmware in the box, but some very interesting things with USB. Adrian Crenshaw has a very interesting website where he's built this proof of concept USB controller that allows for, very obvious at this point, malware to occur, where if you plug it into a machine, it opens up a terminal, opens up an SSH shell to an external unit. If you're in admin mode, you have admin control. But since none of this is really software on a machine, no software on that machine is really going to detect what that keyboard option or that USB option is going to do. There are some discussions to talk about if you've ever used a KVM, which is the ability to switch multiple machines with a keyboard, a mouse, and video, to use those as an exfiltration channel because they are talking to multiple machines. It's very interesting, and this is a very low-cost device. So the idea being that I could implement this in some hardware, leave it dormant for a while, have a timer on it of some sort, and maybe use that. For right now, it's pretty obvious when it occurs, but it's also an interesting attack.
A question,
Yes.
actually. So, exactly, perhaps you suggested that since this is not software, one cannot use conventional techniques. So I was wondering, because of this, then attestation techniques wouldn't work in this context? Because couldn't one attest the BIOS before
So,
executing
and I'll talk
them?
about, TPM signing of
Yeah,
BIOS and
exactly.
cryptographic understanding of the BIOS. And as I said before, we had that one case where they didn't cryptographically sign the OEM image.
Okay, yeah.
So that got owned.
Yeah.
And I'll talk about it now. So if I'm Intel, I'm
Yeah.
going to make, millions of TPM BIOSes. And those TPM BIOSes are going to have private keys in them, right? They're probably all going to be pretty much the same private key. Well, there was a researcher, and his name is now escaping me, that spent 6 months and literally reversed a TPM by dipping it in acid and abrading it and got the private key out. Well, now this person has the Intel private key that's on the TPM that's on a lot of boxes. So from an academic point of view, what is the failure mode to deal with this? Can I reload private keys? I don't know. If I can reload private keys, if I'm a malicious actor, can I reload it with my own private keys? And so the question is, how do you deal with these failure modes? These are not easy solutions. These are really hard things where I'm talking about complex stuff buried into hardware. So yeah, there is some cryptographic control talked about, but the question is to start thinking about, in a failure mode, what would occur in those areas.
Yeah, well, probably Intel should use a different keys for
Maybe
each
they
one.
should, but that could be a lot more expensive, and then who controls what keys, and
Yeah.
then, if I'm working in a specific country, could the country demand those keys? I'm not a legal
Yeah.
person, so I don't know. But these are really hard questions that need academic rigor to start to answer, and I don't know what the solutions are. And so that's part of my presentation, is to convince you that this is a fun place to play and that there's a lot you can learn and add to the body of defensive knowledge. So there are also peripherals that talk directly to the direct memory access unit within the machine. And in 2008, a gentleman named Adam Balow in New Zealand built this lock screen bypass for Windows with a FireWire cable. So you see a machine, it's got the lock screen up, you plug in a FireWire cable, and all of a sudden the screen's unlocked. So it was very interesting, and there are some talks about theoretical attacks based on Thunderbolt, because it's actually a faster version of something like FireWire. And so they're thinking of using these Thunderbolt plugs for things like video outputs. So I bring my laptop here, I plug my video output in, it compromises my machine, and it starts to steal data at 10 gigabits a second. So, I could drain my hard drive pretty darn quickly. So, these things need to be looked at how they would potentially compromise an operating system and what you would do to prevent them. So we've talked about a lot of risks in this. All this bus traffic, most of it is unencrypted and unsigned. And this allows you communication independently between the network and the I/O devices, giving you full read-write memory to disk. Let's change a bit. I'm now admin, I'm not admin. And secondarily, some of the risks are some of the new Intel processors have a very good feature to them. How many people remember the floating point bug in 1995? Does anybody remember that? Okay, what happened was Intel put out, I think, the 486 chip, and it did division incorrectly in certain cases. So what Intel had to do is they had to have a multi-million-dollar recall, physical recall for CPU chips, even though most people didn't physically recall the chip. So what they do allow now is some BIOS code to overwrite and reprogram the microcode in the CPU. So one of the risks is if I own the BIOS, could I reprogram the CPU to do something different? My example is in some of the new chips, they trust the CPU to do AES encryption. So could I do things to the AES encryption that would still look kind of random or encrypted when you put it over the wire, but maybe replace the key with a known key or change the S boxes or do something so that it's not really encrypted? Could I weaken the crypto system in a specific way? Probably not. If someone else was going to unencrypt it on the other end, you'd have to. But the question is, now that I can reprogram the CPU, can I do things that are not good? So the question is, this is all future stuff, right? This isn't really real. We don't have people working in the defensive area. No one is really using this right now. And the answer is, it's probably already on some of the machines you own. Intel has a remote management technology, and it actually, when I received the laptop I'm giving this presentation on, it was actually within this box itself. And it allows for things, some good features like remote keyboard management, remote boot. I can update the firmware remotely. I can do event logging. But as you start to get in, it's got things like a web server that could implement Kerberos. So these are things that need to be looked at by academicians to make sure that they're done with a specific academic rigor. It's a very complicated piece of software. And in 2009, there's another invisible things attack where they actually used the downgrade attack on the BIOS because there was no revision tracking to remap memory to create this -3 rootkit within the system management mode. So this, when they call it -3, this code is actually executed on a separate processor outside the CPU, the ATM code. So you are pretty far deep in the internals of a machine. I think this kind of area is really good to look at from an academic area. And in fact, the remote management software is stored in flash, and at boot up, it's moved into RAM, and it's moved all through the BIOS. So it's in multiple places on the machine. And the question is, how would you see this, and how would you deal with it? So there are some prevention methods that people have been kicking around, and one is maybe we should only have read-only firmware in the end units of laptops. That gets to be problematic when you need to update stuff. I don't know how you do that. If you put machines together for as long as I have, some of the old machines literally had physical jumpers that needed to be pulled if you were going to update the BIOS. Now, most people don't open laptops, and so the question is this something we should do for firmware? Should there be physical jumpers that you have to physically move so that a compromise would require physical access? I really don't know. The other thing is, what authentication do you have to re-image firmware? A lot of the BIOS stuff has hashing built into it and possibly private code, key signing, so they check all kinds of things to make sure that the reimage of the firmware is good, but I don't know if that occurs on other BIOSes on other network cards and stuff like that. Will placing more inside the chip itself be effective? So what you start to see in some of these machines that need to be more secure, I think we'll talk about that in the next slide. So you see them moving it all within a side of a chip so that physical access is more difficult. If you take machines such as the PS3 and the Xbox, some of their security modeling is to take into effect somebody with a soldering gun because they don't want people to steal games. So you don't see that in PCs and laptops. They usually say, by the time someone has a soldering gun, I'm done. But maybe in the future that needs to be, something that we really need to start considering. The next is very expensive. For high-end military equipment, they have trusted foundry where stuff is created at a factory of where people have been vetted and they sign off on that it is the correct machine. And that's a very expensive option, but that is one of the options for pre-owned chips versus chips that could be owned later. And the other thing that people have been kicking around is that virtual machines come with their own virtual BIOSes, and they have special controls in them to control hardware. And can you use those virtualization extensions to add additional security in this space? So some of the prevention methods we talked about is, should we sign updates? And then the question is, what do you do when that key is stolen and reversed or is asked for by legal law enforcement or by nation state? Unfortunately, some of the signed updates for a lot of these machines, some of the people at MITRE who are doing a lot more of the research than I am, to be honest, they're really, really smart. I've learned that these are off by default in many of the machines, so you'd have to go in and implement them. You could do random sampling of either the supply chain or your working equipment to look for timing or power differentials, but that's a lot of work. So that is one of the ways to try to prevent what's going on, so you can see. As I talked, the Xbox 360 and the PS3 implement, and we'll talk about Vista also, encryption options to literally encrypt the bus, so that if I sit there with a hardware tap or I sit there with a card that's not good, that's not supposed to see something, it can't see something on the bus. Vista actually implemented this as one of the options for content protection, so they could encrypt the video all the way from the CPU to the video card out to a monitor, but I didn't really ever see it being used a lot. They used a modified AES structure because they needed it to happen really fast. So in fact, this picture down on the right actually talks about key exchanges and questions that go between, particular hardware pieces within the Vista infrastructure. So the other question is, should we re-engineer the bus architecture on this hardware? Right now, pretty much any peripheral can try to force itself to be the direct memory access master and implement a shim and say, oh, I'm the one in control. So should there be some redesign of these buses, some of them being formal standards and some of them being de facto standards? One of the things that's good in some of the recent Intel and AMD chips is that you have this input-output memory management units that actually say, as a network card or a video card, you can only access this memory. And so you start to see some protections that they're willing to take that small performance hit. And that's actually a good prevention method to have that reference monitor in place. So the other question is, what things could we do to detect? And so one of the questions is, we could baseline all our firmware, and while it's running, and let's say we sign all and the signature fails. Well, what do you do then? There are lots of systems you wouldn't want to have your laptop saying, I'm sorry, the BIOS didn't look right, so I think I'll just not boot up right now. So the real question is, how do you deal with that with availability? How do you deal with that in the fallback? And we have one of the other interesting things that happens in the Chrome OS. We could talk about that. The next is, you can have the TPM sign the BIOS. Now, to be honest, the BIOS starts up the system, so parts of the BIOS need to run before the TPM runs. So the question is, what comes first, chicken and egg, and make sure that small part that runs before the signing part of the TPM that runs makes sense. The other issue being that, once again, what do you do when there's a failure or a mismatch? Do I shut the machine off? I really don't know. So the other concepts for detection are to build some specific hardware that monitors all the direct memory access that goes on at the bus. The question is, where would you put that? Would you put another processor on? It gets back to the old Latin phrase, who watches the watcher. Where do you put these security controls? They're very, very tough. One of the other things that people have kicked around is maybe these drivers and firmware should all be open source so that defenders can be more agile in adjusting against attacks. A lot of these things aren't open source, and when you go look at the conference literature, you have people doing a lot of work to reverse this stuff. It's not easy to reverse it, even with the proper tools. So having it as an open source can really allow people to put more rigor, not just from that company, into these tools, and that could be a good idea. The last one is the host integrity and startup DoD project that's been going on. It measures the OS loaders, and part of the BIOS. It doesn't measure, I don't believe it measures as the machine goes on in time, but just at the boot up, so you could be compromised during the session. But the idea being, at least as you boot up the machine, things are going well, and that's a very interesting, promising research project. So some of the other detection is that, you start to look at if my machine is compromised, maybe with network detectors such as a snort signature or something like that. Maybe I could see it there. I could see it going out. I could see the controls coming. Usually if you see it going out, it's probably a little too late. But at least I can see the command and control network controlling the machine. Maybe I can do that. One of the novel things I'm starting to see is an interrogation where you ask a chip to perform some function so that if they're tampered, the amount of time for them to give you back a bad answer takes longer, and they're lying to you. So if everything is normal, they don't have to do certain activities. But if it's not normal, it takes longer, and the question is, how far can you do that over network jitter or something like that? So the idea being that if I ask you a question and you're lying to me, I would know. I've seen some research in security coprocessors that can't see each other's memory. And so some chips will watch other chips, or sensitive work will be done in one chip and normal work is done in the other. So that gets to eventually a Byzantine general type problem of coprocessors where you have a voting system. Well, 5 chips says the answer is 3 and 2 chips says the answer is 1. So maybe those 2 chips are compromised and not the 5. And so sometimes those voting sessions could be really interesting to detect what's going on. Then we have an interesting cleanup method. So the Google Chrome OS actually put in their documentation how they reload the firmware from a BIOS read. So they actually signed their BIOS. And when that BIOS signature fails, they fall back to the non-rewritable BIOS, which could have its own flaws in it. But the idea, and then it tries to go get a new one so it can re-image. So the idea being that it has a fallback that's read-only and a updatable part. And in many Google updating things, they have 2 updates, a firmware A and a firmware B, you can see in this picture. And so the idea being that if one fails, they fail back to the older version, and if that fails, they fail back to the non-writable one. So if you have the Google Chrome browser, since they update, every 35 seconds now, since they're really good at updating, they actually keep the previous version on your machine. So I've seen some real good stuff. So really the purpose of this presentation is so that you don't underestimate the small. This is a great picture of Moore's Law. Things that are small are not necessarily not powerful. Many of them are, in the parlance of computer science, reference monitors to control things. If you own these things, you can own a lot more stuff higher on the list. And really, once again, I'm suggesting that this would be a really good area ripe for research and frameworks of how to do these things correctly. It's not an easy problem to solve. So does anybody have any questions they'd like to ask me on this situation? Yes?
Now that Macintosh is becoming more popular, what are some of the problems or issues that you've noticed in that area?
So when you look at the Macintosh, they're moving to an Intel type background. And so with some of this firmware, some of those pieces are almost identical to the Intel pieces, and some of them aren't. From some reading somewhere, I know they have a lot of people working on hardware, especially for, tablets and phones and stuff like that. But this is something that needs to be looked at also, because while the malware that targets the OS eventually could be different, underneath the hood, you make, an Intel chip or an x86 chip or a 64-bit chip is a 64-bit chip. And if I own that chip, it may not matter what operating system eventually I'm under. I've owned that system. So, you really want to also look at those things. That's a good consideration.
I have a comment, actually. Really your presentation is very exciting. So I have a comment, really you gave this very clear, impression that the hardware with the related firmware is becoming a large, complicated distributed system.
Yes.
So people focused on solving this distributed system security, between nodes of a distributed systems, but we needed to apply the same ideas at the hardware as well.
So, that's a very good insight. I do agree that as you don't trust these large system
Exactly.
of systems, you can't trust what's in the box, and you may be able to
Exactly.
apply some of those same things
Yeah.
to what's in the box.
Exactly, because for example, we know that we needed to encrypt everything which is transmitted on a network, and so which means you needed to encrypt everything which is transmitted on the buses that you have there.
Possibly,
Yeah, basically.
so
Yeah.
what do you trust, what do you not
Yeah.
trust? And, that's that whole
Yeah.
purpose. So, doing the distributed system security architecture may be very applicable to an individual machine
Exactly.
itself.
Yeah, inside. Yeah.
And you also see a lot of machines that have no hard drive, industrial control systems, stuff like that, that all of this stuff you start thinking about as processors are generic may apply to those things also. They're not, they may not be easily rebootable, they may be fragile. So that, this whole research gets into the, industrial control system
Yeah, we
area.
have done actually also a very good point that I shared the problem that when the bio fail, usually the system stops. And you needed to continue the execution.
Yes.
So we did some work on recovering application line using error correcting code, but it has a lot of limitations. But definitely that is an important area. Okay.
Yes, you have a question?
So you were basically talking that the bias has, or rather the code in the bias has been widely known for many years now. So the question I had is, you have some kind of input devices. It's just that, the way these devices are interacting with our machines have changed. And specifically the bias does not handle all the complicated devices. It just has one, for the visual, which is basically BGAFD, and then one for the keyboard. It has many foreign laws of the OS. So how do you think the BIOS is evolved? When you said it's evolved in a complicated fashion.
Well, when I start to look at the BIOSes, when I started, BIOSes were either non-rewritable, or if they were rewritable, they involved waving a UV light over the chip itself. We're talking, barely patchable or never. And now they've become what many would argue supercomputers in their own realm. If I was in, the mid 80s and said, oh, I just want a computer, it has 4 gigs of memory and this large processing space, they would be like, well, we could go give you this building and it would cost. So I think as time goes on, these BIOSes and these firmware things will take more and more, will be pressed to be faster and faster and do more and more tasks, do more and more defensive measures, and therefore, if you're an attacker, that's the place to be. I'm going to get under the operating system. You look at Intel buying McAfee, right? So a lot of people, when that first occurred, were like, I don't understand. Why is a chip manufacturer buying a security company? Well, they have security protections for their virtualization built into the chip itself. So to me, it's a logical match in that area. So I see these security functions getting driven down into the hardware, and if you're just fighting at a higher level of the OS, you'll never win. You'll never even see it. So this whole deception, counter-deception area is very important in computer science, and if I can compromise your machine without you knowing it, it's a lot more valuable. So that's how I see those machines going in the future. They're going to grow more powerful, and they're going to include security controls.
I have just one more on one of the slides that you showed on GPUs. So when you basically talking GPUs, you said GPUs actually sit with the south bridge, but don't they actually sit with the north bridge?
So some of them do sit on the, now I'll go back to the slide. I think some of them do actually sit on the north bridge, but I think they also have video ports that are on the south bridge. And I'll go all the way back to the beginning of my presentation. And so so if you look at this presentation I have the PCI Express bus off the North Bridge, and then I have a video non-Intel off the South Bridge. So they can be in both places. You know, and once again, these things change so dramatically fast. It's very complicated. When you're talking about supply chains from across the world, it's amazing that these things work together already, but things change rather rapidly. I can get a half a cent difference on a different piece of equipment. It may be different. You know, you take hashes of BIOSes, they may not be the same. You don't know what's in them. You don't know if that's a bad thing or not. If it changes, it could be bad, and you didn't mean to change it, but they're different. It may not necessarily mean it's bad. Does anybody else have any other questions? Well, thank you very much, and hopefully this was good.
Thank you again for this very interesting presentation. It was really something very new for the audience.
Thank you.